Now we move to another method, and we will generate a sine wave using a recursive relation. In this first example, we will get difference equations for our sine wave using the bilinear transform. Let's consider the following system, where we have as an input a unit step, and we have a system, and the output is a sine wave of omega t, where omega is frequency. So if we apply the Laplace transform to the system, we will have this system here, where is the Laplace transform of the unit step, the Laplace transform of this h of t, and the output is the Laplace transform of the sine of t. And when we have such a system, we can see this h of s as the transfer function, so it's the output divided by the input. So the unit step is a very classic signal, and it's 0 if t is smaller than 0, and it's 1 if t is greater or equal to 0. The Laplace transform of the step function is given. This is the general formula for the Laplace transform. So we have a Laplace transform of x of t is this integral from 0 to infinite, our signal times e to the power of st dt. And as I mentioned, the transfer function will be the Laplace transform of the sine, this is our output, divided by the Laplace transform of the input, which is the unit step. So if we plug in here the Laplace transform of the unit step, so we will replace x by the unit step, and we have that it's from 0 to infinity, it's 1, the value as defined in the function, times e to the power of st dt, and this is equal to 1 divided by s. To calculate the Laplace transform of the sine wave, here we will make use of the Euler's formula, and we know that the sine wave, the sine function, can be decomposed into these two exponentials, one with a positive and one with negative sign. So the sine wave, according to the Euler's formula, is 1 divided by 2j, j here is the complex number, times e to the power of j omega t minus e to the power of minus j omega t. And if we use this relation, we know that the Laplace transform for the sine of omega t, it will be omega divided by s squared plus omega squared. And here, if we replace now the Laplace transform of the sine divided by the Laplace transform of the unit step, so the Laplace transform of the sine, the Laplace transform of the unit step, we know that the transfer function is s times omega divided by s squared plus omega squared. But we can also use sin pi to obtain the same results. So here I'm importing sin pi, and from sin pi I'm importing sine wave, the exponential, some symbols, function. Heaviside is the name for the unit step function defined here. And then I am also importing the Laplace transform from sin pi integrals. Now I'm defining the symbols for s, omega, t, z, capital T, and a. Capital T and a we will use later. Capital T will be our sampling period, so the sampling frequency, 1 divided by the sampling frequency, and a will be the amplitude of our sine wave. So what we are doing now is the Laplace transform of the unit step, so it's the Laplace transform of the half side of t, and then we have that the Laplace transform is 1 divided by s, like we obtained from here. Now I want to calculate the Laplace transform of the sine. Now we are including here the amplitude times sine omega t, and the Laplace transform of f is equal to a times omega divided by s squared plus omega squared, like we have here. We're just now having constant value, which is the amplitude here. So it goes out of the Laplace and it appears here. So it's a omega divided by s squared plus omega squared, and we have the same result here. And when we plug in the Laplace transform of the sine wave divided by the Laplace transform of the unit step, this is what I'm doing here, we have the transfer function, which is given here, and it's the same result as we have here, just with the amplitude. So now we have the Laplace transform of the sine wave, and so we reached the transfer function. What can we do next? Now we can make this analog system to a digital system using the so-called bilinear transform.